We're working through, this is 10.4 to 12.3, review number 2. All right, an object moves along the curve. It has position x of t, y of t at time t, with dy over dt is 2 plus sine e to the t. Derivative of dx dt is not explicitly given. At time t equals 3, the object is at 0.45. Find the y-coordinate of the position at time t equals 1. So, if we want to find our final position, we can think of it in terms of starting with the initial, or what's given, plus the displacement. So we want to find the y-coordinate of the position, so everything will be in terms of y. So our final y position is our initial y position plus our vertical displacement, or vertical displacement in terms of y. All right, so we want to find y sub 1. We want to find the position of the y-coordinate position at time t equals 1, and then what's given to us is at time t equals 3, we know what y of 3 is. And then from there, we know that in order to get from our initial to our final, we have to find the definite integral from our initial point to our final point. So integral from 3 to 1 of 2 plus sine e to the t. Now this may look backwards, but we have to make sure that our initial always matches our lower bound, and then our final will match the upper bound. Okay, and then you can use our calculator here. Y of 3 is 5, and then the integral of 2 plus sine e to the t from 3 to 1 is negative 3.731. So in our calculators, there's no need to have to adjust our bounds. We can just plug in that in the calculator, and the adjustments will be made for us. All right, so our final position, y value, is 1.269. Part B, at time t equals 3, the graph is tangent to the line y equals negative 1.8x plus 12. Find the value of dx dt when t equals 3. So this is what we need to use. We need to understand that our slope, dy dx, if we break it down into components, it's essentially dy dt over dx dt. So if we have this equation in front of us, then we'll be able to have a lot easier time trying to figure out where the pieces go. All right, so we know that negative 1.8 is in slope-intercept form. So negative 1.8 represents the slope, and slope is dy over dx. So we know we can represent dy dx as negative 1.8. Okay, we don't know what dx dt is. They say derivative of dx dt is not explicitly given, but we know what dy dt is, which is 2 plus sine e to the t. So if we rewrite our equation here, dy dx is replaced with negative 1.8, dx dt stays, dy dt is 2 plus sine e to the t. And if we do cross product, we can solve for dx dt, which is then going to be 2 plus sine e to the t over negative 1.8. And then if we use our calculator here, or we can just plug 3 in for e to the t, and then simplify that to give us negative 1.636. So this is going to be the rate of change of dx dt, or the rate of change of x at t equals 3. Okay. Part C, find the speed of the object at time t equals 3. So speed is the square root, or the magnitude of the velocity, and the square root of x prime of t squared plus y prime of t squared. So x prime of t squared at t equals 3 we know is negative 1.636, and then dy dt, or y prime squared, we can just plug 3 in for the t in the dy dt, and then find that value, combine those two, take the square root, and we get 3.369. All right, number 2, an object moving along a curve in the xy plane has position x of t, y of t at times t with dx dt and dy dt given. So dx dt is cosine e to the t, and dy dt is sine e to the t. So at time t equals 1, the object is at 0.32, so we're given some information about the initial point, or given point. Find the equation of the tangent line. So tangent line, we need to find the slope, and then we need to find the ordered pair. So we need to, if we want to find the slope is dy over dx, and essentially it's dy dt over dx dt. So we just have to plug 1 in for the t values within each respective equation, and then we get negative 0.451. Okay, so that's our slope. Our order pair is 3, 2. So once we have our slope and our point, we can just put into point slope form, or point slope form. All right, part B. Find the speed of the object at t equals 1. So speed is the square root of x prime squared plus y prime squared. And then we can just plug 1 in for the remaining t's, and speed equals 1. Okay. Find the total distance. So total distance is the accumulation of the speed, or accumulation of velocity. So distance from 0 to 2, square root of cosine, or x prime squared plus y prime squared. Use our calculator and we get 2. Okay. For D, find the end position, our final position of the object at time t equals 2. So we want to locate our components here. We want to find out x of 2 and y sub 2. So we can group all the horizontal component, or all the information regarding horizontal component together, and all the vertical components together. So x of 2 is equal to, now what's given is x of 1. So final position equals initial plus displacement. So displacement from 1 to 2 of x prime, or dx dt squared, or sorry, just dx dt. And that will give us 2.896. Our final y position is our initial y position plus the vertical displacement from 1 to 2 of dy dt, 1.676. So that's our order pair. Okay, let's go to the back here. Number 3, we have let S be the shaded region that is inside the graph of r equals 3. So r equals 3 is an equation that's a circle equation. Okay, and inside the graph of r equals 3, so inside the circle, and also inside the graph of r is equal to 4 minus 2 sine theta. So r is equal to 4 minus 2 sine theta. That's the dimple limison. And we have our graph. It looks like this here. So just to kind of shade in the portion that we want to deal with the area of this region. So inside the circle, and also inside the limison. All right, so remember that when we're dealing with area of polar region, the area is going to be found by building these sectors, or these kind of pizza wedge sectors, from the origin out towards whichever boundary that we choose, whichever graph that we choose. Okay, and also we can use symmetry to help us simplify the problem, and then or just find the area of the portion of the graph, and then either double it, or depending on where the symmetry is. Okay, but first we need to figure out where these intersections are. Okay, so these intersections are going to be needed when we're dealing with our potential upper and lower bounds. All right, so to find the intersections, we're going to set the two equations equal to each other and figure out where they intersect. So we have r equals 3, we got r equals 4 minus 2 sine theta. So if we solve for theta, I can move the 2 sine over, 2 sine theta. 4 minus 3 is equal to 1, divide by 2, so sine of theta is equal to 1/2. So where is sine equal to 1/2? Sine is equal to 1/2 at pi over 6 and 5 pi over 6. So we have 5 pi over 6 and 5 pi over 6. Notice that there's symmetry here. So really, I'm just going to focus on finding the area of this portion in the first quadrant. Okay, so the portion in the first quadrant here, if we're building sectors from the origin, we're starting at 0, and we're going to build these sectors using the circle as a boundary up until pi over 6. And then once we get to pi over 6, once we get to pi over 6, then notice the boundary is going to turn into the limison here. So from pi over 6 to pi over 2, this region is with the 4 minus 2 sine theta. So that will create the area for this region, and if we double it, then we can get this region here. So let's just focus on this portion here. All right, so the formula to find the area of a sector is 1/2 integral from our lower order bound of our radius squared. So from 0 to pi over 6, we're using the circle as we're trying to find the area, the sector area of this circle. So 1/2 integral from 0 to pi over 6 of r squared, and our circle radius is 3, so 3 squared d theta. So that will take care of this portion in the first quadrant from 0 to pi over 6, and then from pi over 6 to pi over 2, we're dealing with this region here, and this region from the origin is we're extending our sector areas all to the boundary of the dipolimicon. Okay, so 1/2 lower bound of pi over 6, and we're extending from pi over 6 to pi over 2 of our radius squared. Our radius is 4 minus 2 sine theta squared d theta. So if we add these two together, we get this portion, and if we multiply by 2, then we can get the two areas together. So we can use symmetry here. And so this formula times 2 will take care of the first and second quadrant. Now notice in the third and fourth quadrant, we can also go through the same thing, but notice that the area that's inside in the third and fourth quadrant is simply going to be a semicircle. Notice that this is just a semicircle. The limicon is not affecting the region in the third and fourth quadrant. So we just need to find the area of the semicircle. So the semicircle is essentially with a radius of 3, and we know the area of a circle is pi r squared, so pi r squared divided by 2 will give us the semicircle, the bottom half of the shaded region, so 1/2 pi r squared. Okay, and we just use our calculator, combine those values together. 24.708 is the area of the shaded region. All right, number 4, find the area of the inner loop created by r is equal to 1 plus 2 cosine theta. So this inner loop is created at the two instances where this graph is going to cross the origin of the polar axis. So when this loop is closed off by the fact of this graph crossing the origin. So to find those polar zeros, we can set the equation equal to 0. So 1 plus 2 cosine theta equals 0. Want to figure out when is the graph going to cross through the origin, cross through the polar 0. So 2 cosine theta equals -1. Subtract the 1 over, divide by 2. So when is cosine equal to -1/2? Cosine equal to -1/2 in the second and third quadrant, so 2 pi over 3 and 4 pi over 3. So that provides the boundaries for the inner loop. So from 2 pi over 3 to 4 pi over 3, the area is going to be 1/2 radius squared d theta. And we just use our calculator or work this throughout by hand, 0.544.